And welcome back. This next lesson is about Hess's Law, which is very similar to the last video that you probably just watched about calculating heat formation and tracking enthalpy in a chemical reaction. So to start in, Hess's Law just states that regardless of the multiple stages of a chemical reaction, the total enthalpy change for the reaction is the sum of all the changes. So it's a way of mathematically manipulating chemical reactions, knowing the enthalpies to just determine how much heat will be exchanged in a chemical reaction. So you should get the same results as your heat of formation calculation from, again, the last video, but it's just a slightly different way of doing it just by reversing equations or by doubling or tripling or cutting an equation in half. So basically applying fundamental mathematics just to chemistry. So what we need to do is for any chemical reaction, we have to have a set of reaction mechanisms. And those are just other chemical reactions of known substances where their enthalpies are known. So sometimes if you consider some chemical reactions will take a very long time to actually react, and therefore it's really hard to track the energy exchange in that chemical reaction. But if you know a group of other chemical reactions that will produce similar products, you can then mathematically isolate those products and determine what the enthalpies would be in a similar situation. So you're basically adding thermochemical reactions together in order to actually track their enthalpy. So it basically goes like this. So if you actually want to consider the formation of ethine, so C2H2, it would require 2 moles of carbon and 1 mole of hydrogen gas. So in this chemical reaction, it might take a while or it might be really hard to measure, but we can figure out the enthalpy by knowing similar reactions. So we happen to know that if you burn ethine, so you have a complete combustion of ethine, it should release almost 1,300 kilojoules of energy. We know that the formation of carbon dioxide will also release, 393.5 kilojoules of energy per mole, of course. And the formation of water will, in the liquid state, will produce 285.8 kilojoules of energy released into the atmosphere. So the way these are set up, now we're basically going to try to create this chemical equation by isolating each one of these reactants and the products so that we can actually figure out how the enthalpy is determined. And so in each one of these chemical equations, we have either the product or we have the reactants hidden inside the chemical equation. We've got a lot of other baggage that we just don't want, and that's where manipulating the equations come in. So when it comes to Hess's Law, we start off with the desired reaction. So 2 moles of carbon plus 1 mole of hydrogen should produce 1 mole of ethine. Okay, and we don't know their enthalpies, so we have to start manipulating the equations. First of all, recognize that ethine is on the product side, but if we look at the first reaction mechanism, ethine is on the reactant side. So ethine here is on the product side, ethine here is on the reactant side. So down below in the reaction mechanisms, this guy is on the wrong side of the chemical equation. And so therefore, what we can do is mathematically, we can just reverse the chemical equation. So we can bring both the products, both the reactants onto the product side, and we can take both the products onto the reactant side. So in other words, we can mathematically reverse the combustion equation. So by doing that, ethine will be on the proper side. So now I have ethine here. But when you mathematically reverse a chemical equation, you have to change its exothermic reaction into an endothermic reaction. So you would have to add energy for this to actually take place. So you're reversing everything. You reverse the chemical reaction here, and you also reverse the enthalpy. So starting from there, we now have ethine where we want it. We have other stuff. We have baggage. That's what I call it, at least. We have baggage that we don't want, but that's where the other 2 chemical reactions come in, because we also don't have carbon or hydrogen. But if we actually look at our other two chemical reactions, carbon and hydrogen are both on the correct side of the chemical equation. So they both should be in the reactant side, and they happen to both be on the reactant side. However, we don't have the right number of moles for carbon. So what we would do next is we would actually recognize the chemicals that aren't actually there. But I also know that carbon dioxide, once I flip that first equation, is on the reactant side. And so therefore, I need to try to balance this off and get rid of the carbon dioxide. I also want to try to get the same number of moles for this carbon right here. So what I can do is I can multiply the entire equation by 2. And that'll give me my 2 moles of carbon that I actually want. It'll give me my 2 moles of carbon dioxide, which I can therefore use to cancel off the unwanted carbon dioxide from my first reaction mechanism. When I multiply the entire equation by 2, I also have to multiply the enthalpy by 2. So whatever I do to these chemical equations, I have to also do to the enthalpy. So when I multiply everything by 2, I'll end up with 2 carbons, 2 oxygens, and 2 carbon dioxides. So typically, if this was a normal chemical reaction, you're trying to balance it, obviously you wouldn't have a whole bunch of 2's there because they would simplify out. But in the process of this mathematics, we're allowed to write it in its non-simplest form in order to actually cancel things out. So from that point on, recognize that I have 2 carbon dioxides on the reactant side of the first reaction mechanism. I have 2 carbon dioxides on the product side of my second reaction mechanism. And so that's like having the same number on both sides of the equal sign when you're just adding and subtracting. So you can just cancel those out. So the carbon dioxides completely cancel out when you have the same amount on both sides of the chemical reaction. My oxygens, however, do not cancel out. On the reactant side, on my second reaction mechanism, I have 2, and I have 5 halves on my product side for my first reaction mechanism. So that's not going to cancel out. So we can only just cancel out our carbon dioxide. That's where our third reaction mechanism comes in, because we want to, we need hydrogen in the end. So here's some hydrogen, and we're going to have to do other things like cancel off this water, and we do need to cancel off that oxygen. So it just happens to have water and oxygen in this chemical reaction. So when I recognize that I need to cancel that off, I will put it down below. All right, I didn't change this equation, so this is the only equation. This here is the only equation I didn't actually have to change. So I just left it as is. I just rewrote it, so that way now I can actually start to cancel things off. So because I didn't actually change my third reaction mechanism, I also didn't change its enthalpy. It just stays as is. So now I can cancel off my water. I have water on both the reactant side and the product side. So I have 1 mole of each, so that will cancel off nicely. Do pay attention to the state. They're both in liquid. That's not a problem for this question, but might be in the future. And I also recognize that 5 halves is the same as 2.5. When I factor it a little bit slightly differently, which means it's great because I happen to have 2.5 oxygens. And so therefore all of my oxygens actually cancel out, right? I have 2.5 oxygen on my reactant side. I have 2.5 oxygen on my product side up here, and then I just cancel those out. Then all you have left to do is just write out what's left, right? So I have 2 carbons. I have one hydrogen rather. So I write those out. And on the product side, I have just your simple ethyne. So once you've matched, so this is very important, once you've matched the chemical equation as the original desired chemical reaction that you were looking for, then you know you have properly balanced and manipulated your reaction mechanism. Once you know you've properly balanced your reaction mechanisms, you can just add up all your enthalpies after this. So perfectly balanced. Add up your enthalpies. In this case, you should end up with 226.7 kilojoules afterwards. So this one is going to be an endothermic reaction. Energy is required for this to take place. And that's really all there is for Hess's law, right? You're just manipulating around your reaction mechanisms. So you basically start to treat chemistry more like math, right, in order to actually balance your chemical reaction. You have 4 questions in your worksheet, in your work booklet. Question 4 is a little bit different. Question 1, 2, and 3, your reaction mechanisms are given to you. All right, so you don't have to do any thinking. Even the enthalpies are given to you. So again, that stuff is just straightforward, figure it out, balance as necessary. But question 4, they don't give you the reaction mechanism. That's up to you to figure out. But it's not too hard to figure out. All you have to do is just find your heats of formation table of values. And if I pick on question A for the moment here, just to kind of guide you through this, I'm not going to do it all the way. I'm just going to set you up. You would look at your given substances. So in this case, you have carbon monoxide reacting with oxygen to produce carbon dioxide. So you have 2 moles of carbon dioxide, you have 2 moles of carbon monoxide. So that's what you have to start with. That's what you're trying to figure out for your enthalpy. If you actually look at your chart, as far as your heat of formation is concerned, in order to create carbon monoxide, it's going to release negative 110.5 kilojoules for every mole. So if I write down a reaction mechanism, I would write out a balanced chemical equation for 1 mole of carbon monoxide. All right, so I just have my carbon and I add it to an oxygen. So oxygen would only come as a diatomic, which means I have to start thinking in terms of half values. So I can do that. Right, and if you don't like that idea at first, then by all means write it out the way you probably would write it out: 2 of this, plus a single mole of this, and then plus 2 carbon monoxides, and that's fine. But if you do it that way, then you're going to have to write out your enthalpy as double this, so negative 221 kilojoules per mole. So I personally find it easier to just not have to do the math here first and just write it out as a single mole of everything. So that's the first equation in your reaction mechanism. The second equation in your reaction mechanism would be for your formation of carbon dioxide. So your formation of carbon dioxide is a little bit easier. You just need 1 mole of carbon, 1 mole of diatomic oxygen, and that should produce 1 mole of carbon dioxide. And your enthalpy is on your chart, negative 393.5 kilojoules for every mole. So now that you have your reaction mechanism, it's just a matter of following Hess's law and manipulate these 2 equations and their enthalpies until you have your desired reaction that you're looking for, just like we did 5 minutes ago. So with that, and for B, C, and D, obviously all of these guys are on your table, at least they should be. Oxygens seem to be the common theme here for every single one of them. As a brief little reminder, we don't worry about our diatomics. They're just made. But everything else is actually on your chart, so it shouldn't be too difficult for you. And if you have any questions, just fire me an email and I'll help you as best I can.